So in the last lecture, in the first lecture, as one of the examples for dynamical systems, I considered a mapping of the two-dimensional torus which was obtained in the following way. We consider the torus as the plane in which we identify points whose coordinates differ by integers. We consider a linear mapping of the plane with this matrix 2, 1, 1, 1. We showed that it generates a properly defined mapping of the torus. And I suggested to understand what happens if we take the classical example suggested by Vladimir Arnold. If we take a cat and we want to see its image under this mapping, so I promised to show the picture. Please come here and look at the picture together. So the square is mapped. It is mapped to a larger figure, and then we identify points, and we see that this poor creature becomes something very complicated. Very well. Let's continue. So we have defined a dynamical system with discrete time. With a phase space X. In this way, it is a map of the product the set of integers in the phase space to the phase space with the properties so that phi 0x is x, phi k plus L x is phi k, and finally for any fixed k, this restriction is continuous. Now we define a parallel object, a dynamical system with continuous time. In a very similar way, we again fix a topological space X, which will be the phase space But now we consider a product of the real line and assume also the same properties. Phi 0x is x, phi t plus sx is phi t. And here usually, of course, we may assume that the restriction of this mapping with a fixed first coordinate is continuous, but usually people assume a little more. They assume that phi is continuous. The mapping with these properties is called a dynamical system with continuous time, or it is simply called a flow. This is a standard term. In parallel, a dynamical system with discrete time is sometimes called a cascade. This term was introduced by Dmitry Viktorovich Anosov, who will appear in our lectures. But this is not so popular in the West. I will not speak much about flows. I want to say only one thing, where they usually appear. Consider an autonomous system of differential equations in the n-dimensional Euclidean space, and assume that f satisfies the standard condition. It is locally Lipschitz in X. Shall I give the definition? For every point there is a neighborhood in which it is Lipschitz, and then we know that for every initial point there is a unique solution. We also know that if x of t is a solution on some interval a b, then its shift is also a solution. But of course, you have to shift the interval where it is defined. So, in fact, this means that if I consider this space and consider integral curves, graphs of solutions, we have this infinite family of similar integral curves. So it's unreasonable to study this large family of similar objects, and usually we introduced the notion of a trajectory. Trajectory is the projection of an integral curve to the space of variable x. So we project all them to the space x. We get a curve in this space, in my simple situation. It has a direction. Direction corresponds to growth of t, and usually we select one integral curve. If we take a point x0, we consider the solution such that x of 0 is x0, like this. And we parameterize the trajectory using this solution. So phi tx0 is the solution with initial data. And then the trajectory is given by the equality x equals 5t0. We project and get the projection. If I assume an addition, we have to assume this not for every system of that type, all solutions are defined on the whole line. But if we assume that for any x0, this solution is defined on the line, I mean the maximal solution, then we get a mapping precisely with these properties. Phi of 0 x0 is x0, so when t is 0, this is the standard basic property or group property of autonomous systems of differential equations, and this is a corollary of standard theorems on continuous dependence of solution of the initial value. The theories of these two objects are almost parallel. If you have some statement which is valid for one of them, reasonable analog is valid for another one, with some special cases when you cannot translate from one language, cannot translate some statement from one language to another. But of course, it is really easier to study systems with discrete time for many, many reasons. But if I want to indicate, I want to show some example, it is easier to show examples for flows, because the trajectory of a flow is a curve. You can see the picture, and the trajectory of this is some set of points. It's not so easy to distinguish sets of points. And one obvious relation between these two kinds of systems Assume that I have a flow phi. I fix some non-zero time t. Usually people call, in this case, call this variable time, because mostly such systems come from applications such as mechanics, physics, and they describe evolution of processes in time. So if I fix, if this is a flow, and I fix some non-zero t, and I consider a mapping of that kind. So what happens for any point x? I consider a trajectory in the flow. Let t be positive. Go along the trajectory time t. This is phi tx, f of x. Obviously, this mapping f is homeomorphism. I can easily find the inverse. Take g of x phi minus tx, and then f of g is what? Phi t phi minus t x, and we apply the second property, the group property. It is phi 0x is x, and the same for g of f. In this case, one says that the homeomorphism f is embedded into the flow phi. And of course, the properties of both dynamical systems are parallel. They are very similar. But you have to be careful. Consider, for example, the simplest situation. I didn't speak about dynamic differential equations on manifolds, but I don't need that. Consider the circle with coordinate x 0, 1, and you identify points. And consider the flow phi tx x plus t model 1. It's very easy to see that it's really a flow. It satisfies all these properties. So you take a point x and go along the circle with unit speed, with unit velocity. And let me perform this procedure. Let me take some t and take fx phi tx. So the flow, I didn't define what is the trajectory of a flow, but it's obvious. So for a flow you have a single trajectory. It's all the circle. But if you look at this homeomorphism, you will see that the dynamics is quite different in two different cases. If T is a rational number, so for example T is M over N, then F to K of X is, it's easily seen, X plus K M over N modulus 1. And you can see that every point of the circle is fixed if you take K a multiple of N. If K is Ln, then F to Ln X, X plus Ln L multiplied by M is an integer. So every point is a periodic point of this homeomorphism. But if T is irrational, then of course you have no periodic points. You shift at some rational number and you never return to the same point. It is easy to see that in this case every trajectory is dense. I hope this is known. I will speak about that when we come to dynamics on the circle. So the behavior of trajectories is quite different. In one case, all the points are periodic, and in another case, you don't have periodic points, but every trajectory is dense. Very well. So we come to the first non-trivial part related to dynamical systems with discrete time. I would call it topological properties. Of dynamical systems, and I will speak about systems with discrete time. So I fix a homeomorphism F and consider the dynamical system generated by F. And of course, many things are true just for an arbitrary topological space. But to simplify presentation, I will assume that X is a metric space. Just to simplify presentation. What is interesting for us? Of course, if you take a finite piece of a trajectory, it's some finite set of points, and there is nothing interesting. So what is interesting is what happens when you study trajectories on infinite segments of on infinite sets of integers, to be exact. And I start with the first notion I think you know it all, but nevertheless I have to define it. So I take a point x and I define the omega limit set. Sometimes people consider it omega limit set of x or of the trajectory. This is the same. Omega of x is the set of limit points of phi to tk of x for all sequences tk which tend to infinity as k tends to infinity. So we fix a point, consider these sequences and take all limit points. Of course, in parallel you can define the alpha limit set everything is the same, but you take sequences of time going to minus infinity. There is a very useful characterization of, I will speak about omega limit sets. Everything is the same for alpha limit sets. I can define the omega limit set in this way. It is, I take intersection for positive n. Is it enough? 1, 2, 3, 1, 2, 3. So what happens? I take my point x, its positive trajectory. I take f to n of x, consider this set, consider its closure, and then I intersect these closures over. And the statement says that this is really the omega limit set. Well, as usual, I have to prove both inclusions. So I show that omega limit set is a subset of this. So I take any point y. I take the corresponding sequence such that since this sequence goes to infinity, for every n, this inequality holds for k large enough. So for any n, this sequence up to some first terms belongs to the this trajectory, and of course then y belongs to this closure because this sequence tends to y. So y belongs to every of these sets, and then it belongs to the intersection itself. And the inverse is also True, of course. Now I take, now I prove this inclusion. So I take a point which belongs to this intersection. What does that mean? Since I take and it belongs to intersection of the closures, so for every n I can find a number t more than n such that distance of ft xy is less than, say, 1n. And now I just take a sequence corresponding, converging to infinity. Say, let me call it Tn. And for this sequence, y, of course, will be the limit point and usually people usually hear one formula's theorem saying that for any x, its omega limit set has the following properties. It is closed, it is invariant, and it is non-empty if x is compact. The first property is a direct corollary of the lemma. We take an intersection of closed sets. They are closures, so it is closed. Invariance. Take a point y in the omega limit set and take the corresponding sequence tk to infinity such that f tk x tends to y. Now if I take any L, then f tk plus lx, I can rewrite it in this way. It is f to L f tk x, but this tends to y, this sequence. F to L, when L is fixed, is a continuous mapping, so this all tends to f L of y, and of course this sequence tends to infinity. L is fixed and tk. So with every point y, the omega limit set contains every point fL of y. And of course the last property is obvious, because if x is compact, you take any sequence of that kind and it has a limit point. And of course, if you do not assume that X is compact, the corresponding statements is false. Take just as X the line and F X X plus 1. Of course, it's a homeomorphism of the line, but for every trajectory, for every point X, its positive trajectory goes to infinity and doesn't have finite limit points. The second, this is the classical thing. The second set related to the general theory is called, I think that omega limit sets were considered by Poincaré. Definitely he worked with them, and definitely nobody before Poincaré studied such problems. The next important set is the non-wandering set. It was introduced by Birkhoff. And I will pronounce this name. It will appear many, many times because Birkhoff did a lot for the general theory of dynamical systems. So we first define a wandering point. A point x0 from my phase space is called wandering. If it has a neighborhood, and there is a neighborhood, and there is a number n such that f to n u intersect with u is empty for n with absolute value. So a point x0 is wandering if you have a small neighborhood such that images of this neighborhood with large positive and large negative indices do not intersect it. And the point x0 is non-wandering. If it is not, and of course it's reasonable to reformulate this in the language of neighborhoods. So we have just to take the inverse for any neighborhood having 0, and for any n there exists n such that it is larger than n, and at the same time f and u intersection with u is not empty. So non-wandering point. You take any small neighborhood, you take any n, and you can find an integer whose absolute value is more than n, such that the image intersects the original neighborhood. One sentence before we make a break. Of course, periodic points are non-wandering. If x0 is a periodic point of period, say m, then the trajectory comes to any neighborhood of 0, just this one trajectory, comes after every number of steps which is divisible by m. But of course they are called trivial, non-wandering points. Of course there are non-trivial points, and we will speak after the break. I want to reformulate the definition of a non-wandering point. A point x0 is non-wandering if and only if there exists a sequence of points xk which tends to x0 and numbers nk going to infinity such that f to nk xk go to x0. Well, of course, this implication is trivial. It just follows from the definition. In any neighborhood, you can find a point like that with k large enough, and then k more than n with k large enough, such that f and k xk belongs to this neighborhood. So, you see, it is mathematical, how to say, illness, or to try to find the most general conditions. So here you can see that you need something like the first countability axiom, but I stay in a metric space. Now I want to show that let dk be the ball of radius 1k around x0 if it's a neighborhood, of course, it's open ball. Using this definition, you can find nk more than k and a point xk in decay such that f to nk xk is in decay. I'm sorry, there is nk such that this is the precise. So if nk tend to plus infinity, then this is the desired sequence. And otherwise, you take points yk. If this is not so, so they tend to minus infinity, you take as yk these points. You take, say, mk minus nk and f mk yk will be xk. They tend to x0. They tend to x0 and indices go to plus infinity. And now a less trivial situation where we get non-wandering points for any x. It's alpha limit set and the omega limit set. Let me, of course I had to introduce the notation earlier. Let omega at f be the set of non-wandering point. This is the standard notation. Sometimes it is called just the non-wandering set. And then we can formulate. So every alpha limit point and omega limit point are non-wandering points. This is also very easy. So let me take this. So I take a point y of the omega limit set. I take the corresponding sequence nk going to infinity such that f to nk y tend f of x tend to y. And for every such point, you can find a number mk from this sequence such that mk minus nk go to infinity. I have a sequence going to infinity, some subsequence, of course. And then if these points are yk, then f mk yk is f m f nk of x. For one moment, I need some. And better to take, say, mk minus mk, okay. And they also tend to y, because I took mk subsequence of this. These guys go to infinity, and we get this situation. But we have to say that there are situations when omega, then the non-wandering set consists not only of omega and alpha limit sets, but it is a larger set than the union. But before that, let me prove the second characterization theorem. The set omega of is closed, invariant, and non-empty if X is compact. The proof is almost direct. If we look at the definition of a wandering point, it is easy to see that if a point x0 is wandering, then every point of this neighborhood U is wandering as well. U is the neighborhood of every its point. So from the definition, the set of wandering points is open, and the complement is closed. Invariance easily follows from the lemma which I had here. So if I take a point y, a point 0, there is a sequence of these points, and a sequence of nk going to infinity such that tend to x0. Then for any fixed L, FL xk tend to FL of x0, and k plus L goes to infinity, and F and k of L xk, it is on the other hand, it's F to L, F and K, xk. This tends to x0, and since L is fixed, this is a continuous mapping. So and the last statement is trivial, because if X is compact, then for any point X, alpha and omega set are non-empty. And here I want to give an example, a simple example of a system whose non-wandering point is more than the union of all alpha and omega limit sets. And as I told previously, it's easier to give examples for flows. So I take a flow in the plane with this behavior. Here I have a fixed point, this trajectory. Here all trajectories are closed, and there is a rest point, and all other trajectories behave like that. It is easy to show that if I take f, this flow is phi. If I take phi 1x, then all these closed trajectories consist of non-wandering points. So the interior of this curve, the interior of the domain bounded by this curve, consists of non-wandering point. The non-wandering set is closed, so this is also non-wandering trajectory. But at the same time, if I take this point R, it does not belong to any omega or alpha limit set, because for these trajectories, their alpha and limit set belong to them. For these trajectories, we don't have. So R is non-wandering, but at the same time, it is not. I'm sorry. It is not. It does not belong to any omega, and alpha and omega limit set. But of course, why it is non-wandering? If I take any small neighborhood, there are trajectories which return to this neighborhood many, many times. And now an important, it is simple, but non-trivial theorem. Proved by Birkhoff. If the phase space is compact, then for any neighborhood U of the non-wandering set, there exists a number T depending only on U, such that for any point x, the number of indices k for which fk of x does not belong to U is not more than T. Well, this is the usual notation for cardinality of the set. This T is called Birkhoff. Constant, and it shows that in fact all the dynamics of a system with a compact phase space is concentrated at the non-wandering set. If I take any small neighborhood, any trajectory lives in this neighborhood only fixed bounded time. Okay, let me take a point x outside this neighborhood U. This point is wandering. All non-wandering points are inside U. So there exists a neighborhood V of x. And the time t of x such that f k v of x intersect v of x is empty if this is just the definition of the wandering point. I keep it there. X is compact, U is open, so x minus U is also compact. So we have an open covering of x minus U by these sets, and I can find a finite subcover. There exists V1 Vn from this open sets from this family, and T1 Tn such that this covers x minus U and has this property. Take T, a natural T such that it's not less than these times, and let T capital be n plus 1 T. So this is the minimal time, and this is the number of neighborhoods which cover. I want to show that this is the desired T. So assume the contrary. What does it mean? There exists a number m more than T, and there exists a point x and indices L1, Lm such that, oh, let me follow my notation. Such that f to L jx So what did I have to show? That for any point the number of indices when its image is outside U is not more. I assume that there is a point for which is more than T, and nevertheless these points are and I take these numbers in this order, and then it's easy to understand that Lj minus Li is not more J minus I. I have integers with such indices. At the same time, if I take, here I have to be accurate, I take these numbers for j from 1 to since where's the neighborhood? M is more than this number. All this L of JT belong to this set. The largest index here is n plus 1t, and it is more, and m is more than. Let yj be f to L jt of x. Every such point does not belongs to x minus u. X minus u is covered with this. So there exists, let me call it WG. WG, one of these sets, such that yj belongs to WG. If I take two different sets, WJ and WK, I assume for simplicity that if I take if I take two indices, say k more than j, then yk is f to L kt x is f L kt minus L jt of yj. Yj is f to plus L. So f to minus L gt yj is just x. But this number is not more than kt minus, is not less. So it is not less than t, because k is larger than j. So if yj, it belongs to its neighborhood j, yk does not belong. We had this, where did they have? The beginning. Oh. For any such set, this intersection was empty if the degree was. So all these sets W1, Wn plus 1, they are distinct. So what happened? We had n neighborhoods, and we selected from them n plus 1 distinct sets, which is impossible.
Excuse me.
Yes?
Is Birkhoff constant any constant for which the inequality holds, or is it just the minimal constant?
In fact, any, because it's enough to have some finite number. You take a neighborhood, and there is some finite number with this property. So if this is the non-wandering set, this is neighborhood, and you consider every trajectory, then the sum of these times is bounded by some absolute constant. I don't know a problem where it would be important to find the least constant. Okay. Now we introduce two properties which are also very important in this general theory. Again, I consider a homeomorphism F and I say that F is topologically mixing. If for any two open sets there exists a non-negative number n such that f and u intersect v is not empty. So if you have two open sets and consider at the positive trajectory of u, it must at some step intersect v, and of course also we can replace, we can exchange u and v. And f is topologically transitive if there exists a point x such that its positive trajectory is dense, the closure of positive it is important to note that in both cases we, in a sense, look at positive trajectories. And there is a very simple example showing that if I exclude here this, then I get a different property. So the example is very simple. Let xb, I take 0, 1, and I take this sequence of points 1 over 2, 1 over 3, sequences of points tending to endpoints. If I take the topology induced from the standard topology, it will be a compact space. And I take just this countable number of points as x. I take f such that f0 is 0, f1 is 1, and here for any point f just moves it to the next point to the right. It's easy to show that we have a homeomorphism of a compact space. And of course, the trajectory of the point is dense. It contains all these points, and when I come to closure, it takes the endpoints as well. But at the same time, for any point x, the closure of its positive trajectory because if I take any point, its positive trajectory will go to the right.
Are you sure about the definition of topological? Are you sure about the definition of topological mixing?
Here I speak about topological transitivity. Why that if in the definition of topological transitivity I replace the positive trajectory by just some trajectory, the complete, then I will get a different notion.
Okay, but
this example shows that. Well, let's return to topological mixing.
Well, I believe that usually people say that f is topologically mixing if there exists, well, some number starting from which this intersection is not empty. Not once not empty, but always not empty. Because what is written here isn't it equivalent to topological?
This is a classical definition. This is a classical definition that if you have two
open sets, they start.
non-empty open set, of course, I forgot to say. Then the positive trajectory of one of them intersects the other one.
And starting from some point, it intersects like always, no?
Okay, it's possible to variate the definitions, but I will work with this too. Now our time is almost over. I will show that for good spaces, topological transitivity implies topological mixing, and for which is more important, it's also one of the Birkhoff theorems, that if X is compact, then topological mixing implies topological transitivity. This is what I will show. And I will, okay, nevertheless, I have a couple of minutes. We know that for In fact, we had only two examples. So what do we know if I consider Bernoulli shift? We have shown that it is topologically transitive. We have just constructed such an element X, and since the phase space is compact, from the theorem which I will prove, will show that it's also topologically mixing. And for the hyperbolic automorphism of the torus, we also have both these properties, but it's not so trivial to prove. This is not so trivial to prove. So this is what will we do in the future.